Welcome back, students. Let's resume. We were doing this equation, and then we ended up with this recursive relation. Oh, I need one more. And r is equal to 1 or r is equal to 1/2. Both cases we get this recursive relations, and let's find out the coefficients. In many cases, it may be impossible to find out coefficients directly, but in the textbook's problem, it is possible. It just takes some effort. Okay, this is a power series expansion with the Frobenius vector t to the r power. And let's see, r is equal to 1 or 1/2, but I decided to do 1/2 case first, so okay, that. So pass it on, what do you get? You get cn t to the n plus 1/2 power. So that is the final form of this answer. And let's find out first several coefficients. Hopefully we can find out a pattern. Most of the times you can, so you'll just have to write C1 equals something, C2, C3, C4, and then just stop there, and there goes one solution, and then you just move on. But I'm afraid you have to do a little bit more here. Anyway, let's go. This is the recursive relation. Plug in n equals to 1, and we get this kind of computation. 1 plus 1/2 minus 1, 2 times 1 plus 2 times 1/2 minus 1. So if you simplify, somehow we get that. And then plug in n equals to 2 and then try to simplify. Plug in n equals to 3 and try to simplify and try to draw some pattern out of these. With some trial and error, I hope you can find out a pattern. 2 times 2 times 2, all those 2's in the numerator, and denominator we have factorial. C3 begins from 6, C2 begins from 4, C1 begins from 2, and then each time I put 2 more numbers in there. So eventually we get 2n factorials downstairs and 2 to the nth powers upstairs. If you want to prove it using mathematical induction, go ahead and do that, but that's not really the part of this class. We'll just put everything in, and then here we go. We have the solution. Excuse me, did I say the solution? No, sorry about that. We have one of the two solutions. One given by r equals to 1/2. Okay, there goes one, and then another one will be b times some power series. That's gonna be the second solution. That's when r equals to 1. All right, let's go ahead. Same recursive relationship here, and then this time r value is 1, so the same same power series expansion, and then Frobenius factor t to the 1 power. So we have t to the n plus first power here, and let's find out those coefficients. Plug in n equals to 1 to this guy, and this time r is equal to 1, so this is n plus 1 minus 1, not 1/2 anymore. So 2 times 1, 2 times 1 minus 1, so we end up with this. And then plug in n equals to 2 and then do some simplification. N equals to 3 and do some simplification. I hope you can find out some pattern. Maybe with some difficulty we're gonna get this 2 times 2 times 2, those kind of things showing up in the numerator, and denominator you have factorial showing up again. In the end, this is what we get, 2 to the nth power, and denominator is factorial for odd numbers. So that's what we get, 2 to the nth power over this 2n plus 1 factorial in the denominator. And what did we have before? We had all the even factorial. This time we have all the odd factorial. and we can put those two together like this. A times the previous solution, B times the next solution. Now, do they really work? Well, I use this mathematical command to actually check out. So summation of this coefficient 2 to the n power over 2n factorial times t to the n plus 1/2 power, and then this one 2 to the n power over 2n plus 1 factorial t to the n plus first power, and that's summation, and use arbitrary constant a and b to get the linear combination, and I asked Mathematica to simplify the left-hand side of that differential equation. You get 0, which means we did it right. As for getting the general term here using the pattern, I have never deducted any point from anybody for failing to see that. Anybody who got the power series and then first 2 or 3 terms ... and then just move on got full credit. And this is what I'm talking about, by the way. Let's see. Yeah, okay, like this, and the first several terms, and name it as y1/2 of t, and then y1 of t for this eigenvalue, and the first several terms calculated out, and the general term I write as y of t is equal to a times y1/2 of t plus b times y1 of t, where y1/2 is a series expansion with first 2 or 3 terms, and then this by1 is the series expansion with first several terms, and I always gave full credit to this kind of answer. If you fail to find out a pattern, kind of like these, don't panic. Just express it in the linear combination form. And of course, y1 and those two series solutions should be in appropriate Frobenius power function. Frobenius power series, not just t to the nth power, but t to the n plus r power. T to the n plus r power. So that's one of the key. And then first several terms, and then the linear combination. That was sufficient as far as my concern. But if you can find out a pattern, this is verification. It's no. This is general solution. If you can find out a pattern and then write the explicit form like this, go ahead. Our textbook author accepts only these kind of closed forms, but I'll accept open forms, so don't worry too much about that. Theoretically speaking, however, in the end, you have to get this linear combination form. A times one solution plus B times another solution.